All right, we good.
Oh, we're starting. Things are happening.
Good afternoon, class. Alright, so today we're talking about matrices, and we've already seen where matrices come from in terms of systems of linear equations. So today what we're going to look at is some basic operations we can do on matrices. So we're going to start with a fairly simple system of equations here. X plus 2y equals 3, and 2x plus 3y equals 7. And I'm going to write the corresponding matrix. Now, can anybody tell me a way we would typically go about solving a system of equations like this?
You could use substitution.
Yep, substitution and go back. Or rearrange one equation and substitute it back into the other one. That's one way. Can anybody tell me a different way if we want to avoid that method?
Try cancelling out one of the terms.
I'm sorry?
Try cancelling out one of the terms.
Yes, we can try canceling out either the x or the y. So in this case, let's say we want to try canceling out the x term. So what I'm going to do is I'm going to multiply the bottom row here by negative 1/2. That transforms this into the following set of equations. So we have, first equation stays the same, and then the second equation becomes negative x minus 3/2 y equals negative 7/2. And see, somebody else, what can we do next once we have this, we've come to this part? Yes, we can add the two equations together. And this gives us 0x plus 1/2 y equals negative 1/2. And then this resolves, obviously, to y equals negative 1. Now we can do similarly to find out what x is by canceling for y. To do that, I'll multiply the bottom row by negative 2/3. And the bottom row becomes negative 4/3 x minus 2y equals negative 14/3. Then we add our two equations together, and we get negative 7/3 x equals negative 5/3. So x equals 5/7. I believe that's right. Alright, now, if we want to try and translate this into operations on the matrix, can anybody tell me what kind of operations we did here? Like, try and isolate, a portion of what we did. Does anybody have any ideas? Yes.
So we multiplied one of the rows by,
Yes.
I guess,
We multiplied one of the rows by a scalar. And that is one of the three basic row operations that we can do on a matrix. So in the first case here, we multiplied the second row by the scalar negative 1/2. That allows us to cancel out one of the things. Along the same line, another thing we did was we added a multiple of one row to another row.
Sorry, I think the x is wrong.
The x is, I'm sorry?
The value of x is 5. Something.
Right in here?
Minus 1/3x, or not 7. 1, not 7. Next.
Down.
Yeah,
Oh,
yeah.
you're saying that this is, because we have, let's see, we have
3/3.
1x minus 4/3
So
X.
negative 1/3.
equals, oh, you're right, yes, I'm sorry, negative 1/3 x. Thank you very much. Alright, so we multiplied one row by a scalar. Second, what we did was we added a multiple of one row to another row to solve for what y was. That's another thing we can do. We can add a multiple of one row to another. Alright, and then thirdly, the last row operation. Now, does it make sense to everybody that if we were to take the two equations and swap them around, that we would still get the same answers? Same answers for x and y. X and y are going to change if we switch the two rows. So we can swap any two rows with each other. Alright, so if we apply these operations to this matrix, what we're going to try and do is reduce this matrix so we come out with the answers for x and y, and we're going to kind of see what that matrix looks like and see what we can kind of expect when we do row reductions on these matrices. So for the first one, we had multiplied the second row by negative 1/2. So if we do that on this matrix, the matrix is going to become negative 1. So now this bottom row becomes negative 1, negative 3/2, and negative 7/2, which is again the coefficients over here. Alright, next, if we add these two rows together, that should give us, or actually what we're doing here is we're adding 1 times this row to the bottom row. So it's the bottom row that's being changed, not the top row. It's very important to keep that distinction in mind. So we add them together, we get 0, a negative 1/2, and a negative 1/3. Negative 1/2, yeah. Positive 1. Alright, there we go. That's the math straight out. So that turns into this matrix. That makes sense to everyone. Alright, and finally, what we are going to do is, what we have here is we have 1/2 y equals negative 1/2, so we turn the coefficient of the y into a 1 to find out what the other side is here. So we're going to scale the bottom row here to make this coefficient 1, and then this should hopefully come out to the desired negative 1. So to do that, we multiply it by 2. So multiplying the bottom row by 2. Gives us, on the bottom row, we have a negative 1 over here, as we desired. Does that make sense to everybody? Is everybody following where that's coming from? Alright, and then finally, we want to solve for x. Now, does anybody have any idea what we can do here on this matrix to solve for x?
Multiply the second row by -2 and add it to the first.
Yes, we can do that. And the reason for that is, which I'll point out kind of why we do that in a second here. Now when we do that, we get a 0 in this position and a 5 over here. Now in effect, what we've done is we've turned this system of equations here into a new system of equations here. And the new system of equations, which we just kind of read off here, tells us x plus 0y equals 5. And 0x plus y equals 3. That way what we've done is we've turned the coefficient of the variables corresponding to the x into 0 in one of the rows, and the coefficient of the y in the other row into 0. So we get two equations, which just reduces to x equals 5 and y equals 3. Does that make sense to everybody? Why that works? Alright. Does anybody have any questions on that?